we can start with the first slide. So just a few words on myself. I'm very happy to see that there is about 50 people already in the call. Great to see that interest. My name is Hillig. I'm a laboratory head in structural biology at the Nuvisan site in Berlin. So I started chemistry some long time ago and then moved over into protein crystallography and have since then been and are still a protein crystallographer in the structural biology unit here in Berlin. So today it's about targeting RAS via SOS and mainly about the impact of biophysics and structural biology in such an lead discovery project. I think the next slide is the agenda, just a quick introduction at the beginning on RAS and SOS. And then you will see that we attack that via two different approaches, via a fragment screen with NMR and followed by fragment hit characterization with different biochemical, biophysical methods, and in parallel a high throughput screen, which again we analyzed with lots of co-crystal structures and lots of biophysics to understand what we have found there and how we can optimize it. Basically, then comes a merging of the two approaches and cellular characterization of a probe that we have actually released into the scientific community. And all questions, you can type them in your Q&A window, and we will deal with them at the very end. Just one slide on housekeeping rules here. Your microphones should all be muted. Please use the Q&A box for any questions. I try to have an eye on that, and we'll certainly look at this at the end when we come to the questions. The session will be recorded, and we will be very happy. My colleagues here at the administration of Nuvisan will be very happy to supply you with the slides afterwards. I think there will be more information on that afterwards. Now, just to get an idea who those people are that are on the other side, we wanted to start with a quick poll here where we just wanted to see, did you work already with Nuvisan or did you hear about Nuvisan? What was your connection so far, or is that your first contact with us? I think we can give that here another 10-15 seconds, and then we have a first idea who you all are and what your connection to Nuvisan so far is. There is now the answers. Did you collaborate? Yes, for early discovery solutions. Okay, 13%. For clinical solutions, 1 out of 50. Never worked with Nuvisan. That's also good to hear for us. So it's nice that you get in contact with us. Never worked. No, however, I worked with Roman. Okay, that's nice. 2 people that worked with me. That's nice. Thank you for that first feedback. Better to have an idea about you than just talking against the screen here. So I think I go to the next slide. One overview on basically where I am sorted in the bigger picture of Nuvisan as a CRO. Nuvisan has a longer tradition to be a CRO for drug development that is going on for many, many years. The drug discovery platform that we now have in Nuvisan was actually acquired from Bayer some 2 years ago. So up to 2 years ago, about 400 people that are now Nuvisan were Bayer employees, and then Bayer handed us over, but from my point of view in a very, very good way, namely as a complete drug discovery platform. We have everything from biosciences, making the proteins, analyzing proteins, biophysics, structural biology, to a very large screening department with a very good screening library, to the chemistry department that you need, to DMPK and tox, digital life science, and also pharmacology division. So the whole package with about 400 people was handed over to Nuvisan, so that now Nuvisan has a very strong drug discovery platform, basically only 2 years old, but with probably in some cases decades of experience in drug discovery, in early drug discovery. So then to the actual topic of our talk. I come to this case study that is very close to my heart in a moment on the next slide, but basically why biophysics is so much in the focus of that talk and also here in general. Basically, we have state-of-the-art technology in Berlin here at our research site, all the different biophysics methods that you usually would use. And when I look back, I started about 20 years ago in pharma. as a crystallographer. And at that time, we got the hit lists on the table. We got the top compounds from the hit list on the table and started trying to co-crystallize them. But we did not have the means to validate whether those hits, let it be a few hundred or just a few tenth or a few thousand nowadays in a hit list, whether those are actually true binders or whether those are mainly false positives. So from the mid-2000s on, we started to install all the biophysics that then slowly was growing up everywhere. Basically, the most important point from my point of view is hit characterization, finding out whether an HTS hit is a true binder, a specific and true binder, or whether it's a false positive and should rather be dropped. That can be extended then in mechanism of action studies when you have interesting targets where you are not sure which domain or in which way it activates or deactivates. That can go, of course, then also into SAR support when you have a lead series and you want to further optimize it and want to find out whether it's entropy or entropy driven, for instance, via ITC. But you can use those methods then also for screening. A very easy entry screen is, for instance, the thermal shift assay, so screening for thermal stabilization. And we do that even with the high throughput library with several hundreds of thousands of compounds. Basically a kind of a gold section and a focus section of our 3 million compound high throughput library. And you can also use a couple of those methods as entry assays in fragment screening. If you don't screen directly in crystals, which you can of course also do, which we also do, you can also say, I first want to expose a fragment library via thermal shift stabilization to the target or via SPR or via NMR. So all these methods have become super important. And today, a number of those topics now will show up in this RAS SOS story that I'm to show you in a moment. Hit characterization, SAR support, mechanism of action. So now into our case study, RAS and SOS. And from this slide on, there is the Bayer logo here in the upper part, because this story was actually coming from our joint Bayer history and was also published. But most of the colleagues, or many of the colleagues that actually drove this project, and mainly also in lead discovery, are actually those that are now at Nuvisan. So it's very good that we have this case study here, and very kind of Bayer to allow us to show this here, to give you all an idea of what can be done in early lead discovery. Okay, off into RAS. So RAS is a molecular switch. Most of you will know there's an inactive state bound to GDP, an active state bound to GTP, and there are 2 helper proteins that help to switch on that switch. There is the exchange factor, which is SOS1 in our case for RAS, that helps RAS to let go of GDP and GTP from the environment. Excess of GTP can go into the molecule and then it's switched on. And there's another helper, that's the GTPase activating protein, that complements the active site. Then hydrolysis can take place and then you are back in the inactive state. Then basically, there's 2 mobile regions of interest. The whole protein is pretty rigid, but 2 regions are by evolution, by definition, very mobile. That's the switch 1 in orange and the switch 2 in blue here. And they have to be very mobile because they indeed switch, they indeed sense whether the gamma phosphate is present or not. So when GTP is bound, the switch 1 folds in, the switch 2 folds in, and those 2 adopt then the one and only active conformation, which is also crystallized here in this 1990 crystal structure. And then the effector proteins sense that the switches are in this one and only active conformation and can do start their signaling cascades. When it's back into the inactive state, then the gamma phosphate is missing and switch 1 and 2 can relax a little bit and can form several inactive states, which are then not recognized by the effector anymore. Now, why does pharma look into RAS? Of course, and does so for already a very, very long time. The background is that many human cancers, here the number seems to be 10 to 30%, have RAS mutations, and those are then usually activating constitutively active mutations. And they are mainly, now that you know about the switches and them sensing GTP, it's natural that they are also in those immediate environments. Usually it's Q61 in the switch 2, or it's some G12 position, which is here in the P loop over the phosphates. And if patients develop those mutations, then the GAP usually can't bind anymore, and we stay in the GTP state, and cancer has a chance to signal all the time. Now, why was basically RAS the prototypical undruggable target until just a few years ago? The background is that it looks a bit like a billiard ball here. There is not much in terms of pockets. There is this very nice and deep pocket, but there is picomolar affinities to the nucleotide. So I think still the consensus is that it's hard to fight against GTP when it binds picomolar and there is millimolar concentrations in the cell. So this pocket basically probably most likely doesn't work. And only recently people discovered that there is a switch 2 pocket under the switch 2 that was not so really in the public knowledge when we started this project. And we started this project on one particular mutation, G12C, because we were at the time focusing on lung cancer. And so you will see then when it comes to RAS, always the G12C mutation on the next slides. So what did we do at the beginning? We were aware this is a very undruggable target. So we switched our focus to the interaction partners, the nucleotide exchange factor, SOS1, or the GAP. And then the point was a bit for us, the GAP is not active anymore, so you would need a small molecule that enables this complex that has trouble to form with the mutations to form again, which looked a bit like an even higher hanging fruit than interacting with this or affecting this complex, where the idea is you in hyphens just have to break that protein-protein interaction to stop that exchange and then to stop RAS in its tracks here. So this is what we did. We focused on this upper part, on SOS, on the SOS-RAS interaction. And in order to increase the probability of success, we did so in 2 different approaches. We started with a fragment screen, where we said, and there's precedence in literature, even for an exchange factor of ANO some long time before, that you can lock such a GTPase in a dead end complex with its exchange factor with a suitable small molecule. That would be then in our terms called a stabilizer or dead end complex, and in the years in between also the word molecular glue came up for that idea. You glue those 2 together and take RAS out of the equation. The other approach was a more direct one, namely going for a high throughput screen where you screen for the enzymatic reaction, where you, so to say, check whether SOS is able or not anymore to exchange, to kick out GDP and allow GTP to bind. This is more agnostic. You don't care then whether it's by binding to RAS or to SOS or to the complex, whereas in the fragment arena, we needed the complex to start our screening activities. I think I want to go, now with the next slide, first in the fragment screen. The fragment screen is either you directly screen in crystals, or the first step is finding the fragments in some method, some biochemical, biophysical method, and then doing the crystal structures in step 2. At the time, we went via this 2 approach. So we used another method, not crystallization, to find the fragments. And in this case, we went for ligand-observed NMR, STD NMR, in cocktails of 8 with a large library or a typical fragment library. Like fragments are usually in the range of 1,000 to 3,000, I guess. And this was here a 3,000 fragment library. At the time, we did that with the colleagues at Evotec in Hamburg, very good collaboration. In the meantime, we ramped up our own NMR capabilities so that we have all this now also, of course, in-house. At the time, at this early point, we made that complex. We characterized it that it is there, and it's actually in the absence of a nucleotide a very tight complex. I think the KD is about 30 nanomolar between the 2 proteins. Was easy to purify it and ship it to Hamburg for the NMR screen. At that time, I was not actually too hopeful how much we got out of that. I would have been happy with a handful or 2 handfuls of hits, and that would have been enough to actually start a project. To our surprise, we found a 10% hit rate. Out of 3,000 fragments, 300 showed binding. And binding would be the 1-dimensional NMR spectrum of that compound. I show you here already our best hit. We call it here fragment 1. And in solution, it looks like this. And in this STD NMR, you magnetize basically the protein. And then if the small molecule or the fragment binds to the protein, you get a signal, and only if it binds. And we got that here with the KRAS SOS complex, that you get the spectrum that you expect from the free fragment. Now we had 300 of them, and that is way too much. I would even now say to co-crystallize them all. So we got a bit more strict and said, okay, we want those glues. So a glue needs to bind to the 2 and should not bind to RAS alone and should not bind to SOS alone. So we basically submitted those 300 in 2 more STD screens and screened them all on RAS alone and on SOS alone, and then kicked out everything of the 300